Hello, everybody. I presented two constraint community detection modeling approaches with applications. Community detection, CD, is a process of identifying groups of nodes within a network with stronger connection with the group than with nodes in other groups. Community detection finds application in social network analysis, biology, computer science, urban planning, etc. Constraint community detection as a generalization of standard community detection finds application in fields like cybersecurity, where the incorporation of specific constraint enhances the identification of hidden communities or anomalies within networks. We consider and investigate the constraint community detection CCD problem, but I start with standard problem and its generalization. As input in CDP, we have an weighted network G given by adjacency matrix W, and also we have a number K of desired community or exact number of communities. As output, we expect a partition C of nodes into communities, or assignment of nodes to communities. Objective function was chosen a popular measure called modularity and given by Formula 1, where weighted degrees of nodes are present, and indicator function. So problem one, it's standard community detection problem asked for such node assignment that maximizes the modularity. Variables in this problem form integer vectors represented communities, certain communities, and there are some constraints such as labels of communities have to be in the range 1 to k. Second, that this is a partition, so the constraint for must hold. Symmetry constraint that if U in the same community as V, then V in the same community as U. Transitivity constraint, if U and V in the same community and U and W in the same community, then V and W is also in the same community. If U and V in the same community, but U and W is not, then V and W is also in the different community. And also the constraint can be present on all the communities are non-empty, so the constraint 8 holds. There is a moving to constraint community detection problem, CCDP. There is a list of some constraint present can be found in literature, such as community side constraint, balance constraint, seed node, or labels, conflicting, forcing, etc. In terms of communities, and they can be represented in the following constraints, where, for instance, this means that there is a bound on the size of the constraint. Here, balance constraint can be different, and here there is one of such constraint where we have an upper bound on difference of size of two communities. Then seed nodes represent as a requirement that some vertices has to be assigned to a certain community or a certain set communities. Conflict in constraints represent requirement that some vertices have to be in different communities and forcing in the same communities. Standard community detection problems normally are solved by effective heuristics. If the additional constraint, like I mentioned above, are present, then it is complicated to incorporate them in the heuristics. That is why in most cases transmission to consideration of binary optimization problem is made. And this is one of way to do the transition, where this is standard approach, where variables form a matrix Y, where YUV equal to 1 if nodes U and V are in the same communities and 0 otherwise. In this case, the objective function takes form 16, which is linear function, and our objective to maximize this, it's this we called problem 2. And this is standard community detection constraint can be partially represented in terms of these variables, such as symmetry constraint and transitivity constraint. Partition constraint hold because of the way of assignment of vertices to communities based on non-zero elements of matrix Y. And but constraint 3 and 8, where the directly size of communities are present, cannot be written in terms of Y, which is a disadvantage of this modeling approach. Moving to the additional 5 group of constraints, it turns out that only 2 of them, which is conflicting and forcing constraint, can be written in these terms, while other 3 are not. So in total, if we consider the constraint community detection problem with all the constraint, only half of them can be written in terms of Y. That is why if all the constraint or most of the constraint are present, we need to use other approach. And that is why we move to our approach, where modeling is made in terms of other binary variables. They form matrix X, where elements X, U, G equal to 1 if the vertex U is assigned to community G, otherwise is not. Is rewriting the objective in terms of these variables, we come to this expression, which is quadratic objective function, and our goal to maximize the function, which is problem 3. Also, in order to we have to incorporate the additional constraint called one-hot constraint, taking form of 24. And now we review how to the CC community detection, standard community detection problem can be represented in terms of this variable X. Condition 3 holds automatically, meaning that no other communities other than in range 1 to K can be assigned. Then partition is also is performed because of present of one-hot constraint, is ensured by one-hot constraints. Symmetry constraint hold automatically, so they are redundant constraints, the same as transitivity constraint also are redundant. And finally, the last constraint on that all the communities are non-empty can be written easily also in the following as the following inequality constraint. And finally, there is a list of formalized in terms of X additional constraint, which we called problem 3G, generalization of problem 3. And first is community size constraint. We have linear, we write it as a linear constraint. Balance constraint takes form of quadratic constraint. Seed nodes, linear equality constraint. Conflicting enforcing as a quadratic equality constraint. On total, problem 3 is a problem with linear constraint and quadratic objective, which can be solved by the corresponding quadratic solvers, quadratic optimization solvers. This the presence of these two non-convex constraints made impossible to use these solvers, but nonlinear solvers can be used for that. In terms of dimension, second problem is better. So the conclusion, the presented paper attacks the critical task in network analysis called constraint community detection, CCD. A new approach to mathematical modeling this problem is presented, expanding the set of formalized constraints. A comparison with the standard modeling approach is made, demonstrating the advantages of the approach. Both approaches, standard and tower, can be combined, forming new CCD models in the form of polynomial binary optimization models. Nonlinear solvers can be used to solve them. The CCD model also allows the reduction to popular CUBA models, which are solved effectively by quantum and digital annealers. Thank you for your attention.